I'm Sanjeev Arora, Professor of Computer Science here. And it's my pleasure to introduce the first speaker this morning, David Harel. David is a Renaissance man in the best tradition exemplified by Alan Turing. He's well known for his work on logical specifications of man-made and natural systems. He's famous for his invention of the graphical language state charts, which became part of the UML standard. He's also known for his work on dynamic logic, an extension of modal logic used for formally reasoning about computer systems and other systems. More recently, he has become interested in modeling and analysis of biological systems and is working on a computer model of a nematode, which was the first multicellular organism to have its genome sequenced. For his pioneering work, David Harel has been awarded many prizes, including the ACM SIGSOFT Outstanding Research Award, the ACM Software System Award, and ACM Karlstrom Outstanding Educator Award. And last but not least, Israel's top civilian honor, the Israel Prize. I should mention that Israel is one country in the world where the computer scientists are the celebrities. Here in the US, if you ask a person on the street to name a computer scientist, they'll probably respond Steve Jobs or Bill Gates. But in Israel, the person on the street will probably respond with the names of two of this morning's speakers, and maybe the third in the afternoon, David Harel, Avi Vigderson, Shafi Goldwasser, etc. At least I'm told this is what it was like 20 years ago. Maybe Israel is becoming more like the US now. David is a celebrity in Israel not only for his research, but also for his numerous expository articles, including in newspapers, as well as his television program on computer science. Please welcome a true computer science pioneer and celebrity, David Harel.
Good morning. The worst thing was to miss yesterday and the day before yesterday, but yesterday I was in Edinburgh giving a similar talk. So it's all because of Turing. He was both in England and in the United States. By the way, you mentioned Steve Jobs and Bill Gates, and the story goes that they met, and Steve Jobs said to Bill Gates, you know, I had this dream last night. God came to me in my dream and told me I was the Messiah. So Bill Gates said, I did not come to you in your dream last night. So I'm going to try to do something kind of personal. So here's a giant with a dwarf on its shoulders. And this is a saying attributed to Isaac Newton, and it's probably the case that he wrote this or said this, but he was not the first to use this aphorism. And if there's anything that I'd like you to take away, a single thing to take away from this talk is go and read this wonderful book, if you haven't read it yet, by one of the greatest sociologists of the 20th century. It reads a little bit like Umberto Eco's novels. It's almost like a mystery book full of wisdom, and you'll see that hundreds of years before Newton, this aphorism was used. So you've probably heard a lot about Turing in the last 2 days, so I'll just whisk very quickly through a few slides here. Definitely the father of computer science. I like to say that he was almost the Mozart of computing, died at a young age, leaving an unbelievable legacy. And one of the things that I think probably came up in some talks here also, in Edinburgh, it came up a lot. What would he have been doing had he been still around with us? Conceived of the simplest, all-powerful models of computation, but at the very same time worked on the design of some of the most complex computers of his time. As we all know, proved that many things computers cannot do already in 1936, which is amazing, but also taught us that there are some amazing things that computers can do. He also did the pioneering work on mathematical and computational modeling of biology, morphogenesis specifically, but also, of course, dealt with the question of us and whether computers can be intelligent like us. And I really and truly feel that this year is just the start of a big effort to get people to recognize the greatness of this scientist. And in a way, I think his impact on humanity's day-to-day life is greater than any of these, but definitely he should be mentioned in one breath with. So that was the giant. And now to us. So many of us feel that a lot of our work is really standing on Turing's shoulders and doing just a little bit more in those directions. And so that's what I'm going to do this morning. I'm going to talk briefly about three things that Turing did, all of which or at least two of which I'm sure you know about very well, and one maybe a little bit less, and the way they impacted one average computer science career, which is my own. But I added this next slide also because yesterday before my talk in Edinburgh, there was some journalist who interviewed me. He said, we have half an hour, and I'd like to talk about what you're going to be talking about in your talk. And for 25 minutes, he talked to me about state charts and software engineering. But then I said, I'm not going to even mention that stuff in the talk. So he said, well, we have no time left. So I said, you know, it's your problem. So it really goes around, but doesn't touch upon maybe this more, at least better known parts of my work. So, so the first part is computability, limits of computation. And of course, Turing was one of the 2 or 3 people who did the most important work, perhaps the most important work on computability, universal computing, non-solvability, and really is the key figure in establishing the absolute limits of computing. And I'm going to mention one in slightly more detail and two in much less detail, 3 lines of work that I have been involved in over the years, which all can be viewed as direct continuations of Turing's work: computability on finite structures, on recursive structures, and quite a bit of work on high undecidability, high non-solvability. So again, I'm going to do this very briefly, but I presume you know this, but there's a reason for going through these few slides. So I love this quote. It's from many years ago, and the quote is not from a person off the street. It's from the editor-in-chief of a software magazine, who says, as you can see, put the right kind of software into a computer, and the software will do whatever you want it to. There may be limits on what you can do with the machines, but there are no limits on what you can do with software. I was born in England, and my parents tried to bring me up as a polite English boy, at least up to the age of 7 when I went to the Middle East, and everything shattered. But if I were not brought up in England, I would say bullshit. But I was, so I won't. I'll just say that. And of course, it's not because this person missed out on something he should have read or should have known about. This person is an absolute ignoramus about perhaps the most fundamental facts in his own profession. And one of the great things that Turing and Church did for us was to replace the division between things we kind of are able to do and not able to do because we're not rich enough or not smart enough, and replace that with the fundamental dichotomy between problems that are solvable, decidable, and those that are undecidable. And when I give talks to to less sophisticated or less computer science-oriented people, there are 2 questions you can ask about this line. One is, who gave you the right to even draw a line there? You know, I have a Lenovo something 500 or other, W500. Maybe you have a Cray in your back garden. Maybe I cannot do something, but you can do it on your computer, and so on. And so the Church-Turing thesis teaches us, and this is a version I like of the Church-Turing thesis. I think this is much more dramatic and better understood than you can do everything with the Turing machine. All, you know, object-oriented, graphical, animated UML is exactly the same as my laptop or whatever. And the second question, of course, is once you've jumped up and down dramatically and, you know, pointed to the fact that this line is extremely robust and it has not changed since the 1930s and probably will not change at all, then the second question, of course, is maybe our friend from Time magazine is right and everything is, in principle, at least down there, and the answer, of course, is no. And my favorite example of an undecidable problem, which those who recognize it will know that it's not exactly the halting problem, but the reduction to it from the halting problem is not that difficult, and that's the tiling or domino problem. And so you want to tile your living room, and you go up the main road in Princeton, and there's this shop, and you walk in, and lo and behold, instead of tiles with fish and birds and rainbows and stuff, you get tiles that look like this. And there are a finite number of types of tiles. There's an infinite supply, there's an unbounded supply of each of the types of tiles. But this guy selling you these tiles has this crazy contract you have to sign, which has 2 clauses. One is you're not supposed to turn them around or flip them over, which, by the way, is not an issue. It just makes the presentation a little easier. But the main clause is you have to sign it whenever you tile, the edges on touching edges have to have the same color. Okay, so here's an example. Let's say these are the only 3 types of tiles that you have, and let's say you ask yourself the question of whether you can tile any sized living room with this set of tile types. And if I gave you a piece of paper in a few minutes, you'd probably come up with this, which is a legal tiling. It can be easily extended in all directions, and it adheres to the rules. However, if we make a change and swap these 2 colors, again, it's not too difficult to give a little proof that you cannot even tile a small living room, and I'll leave this to you. So these are kind of nice little puzzles. We could have made them a little more difficult, but in computer science, we're not interested in puzzles. We're interested in the general question. The general question is, given a tile set T, can this tile set, finite set of tile types, tile any sized area? And just as a tiny little homework assignment, the question of whether you can tile any K by K living room is equivalent to the question of whether you can tile the infinite plane. One direction, of course, is obvious. If you can do the infinite plane, you can do any living room. The other direction is not quite obvious, but it's a nice little exercise. And of course, the punchline here is that there's no such thing. And again, this is not the kind of audience I have to get up on the table and jump up and down, but some audiences you do really have to do that and say, don't go trying this out. You know, if you limit yourself in this way or that way, then yes, this is, and it's not doable because we're not smart enough. No one, when I'm finished here, no one will go outside and look for triangles that have equal sides but don't have equal angles, although no one has ever measured or looked at all the triangles in the world, because we can prove that there aren't such things in exactly the same way. We can prove. And this particular example is due to Wang, 1960s. And the halting problem we're all familiar with. This is a very easy program to determine which of the reals it halts on, of course, exactly the positive integers. And if we now restrict ourselves to the positive integers, we can write down a much more interesting little program, which is a 3x plus 1 program. And I hope you're all familiar with it. And no one knows, this is open as far as I remember since the 1930s, as to whether this little program halts on all the positive integers. So of course this is a very boring example, this is a very interesting example, but this is interesting to, say, number theorists. It's not, in principle, not interesting to a computer scientist. A computer scientist is interested, again, in the general problem, which is, can we solve the general halting problem, which is given a program in some officially defined language, an input, yes or no, if it does or doesn't halt. And this, of course, is due to Turing, that this is undecidable. And now the next thing on this slide is something that I would really like to hope that everyone here has heard about and knows about. And not only that, but recognizes the profound nature of the next statement, but I will jump up and down and make a big deal of it anyway, and this is Rice's theorem. Not only is halting undecidable or equivalence or correctness, but nothing is decidable about computation. So unless the question is about the syntax, I mean, does this program have 1,000 lines, or unless it's a trivial question, which is always a yes or always a no, Rice's theorem does not say that there are many undecidable problems. It says any statement, any non-trivial statement about computation is going to be undecidable. And for me, this is the first time I kind of understood what this meant. You know, this puts us all in the computing profession in the position of being the prime example of the barefoot shoemaker aphorism. I mean, we cannot compute anything about computing, which is our profession. And this is amazing. And if you know how it's proved, it's kind of clever, but again, it builds on Turing's work direct. And now getting to the dwarf, which in this case is me, I'd like to talk first about computability over finite structures. And I have a reason for showing this, not only because it fits in nicely, but because Ashok Chandra and I are very proud of this work. So it appeared first in the stock conference and then in journal version. Can you guess which one is me? A little bit of a problem up there, which has changed. Ashok actually hasn't changed that much if you've seen him recently. It's just got a little bit grayer. And the reason I'm going to make a little bit about this is because the papers, both the conference and the journal version, were written in the setting of relational databases. And the title was Computable Queries on Relational Databases. And I know that many people in theory of computation are not familiar with this work, and we think you should. So I'm going to show you some original slides from the Stock Conference of 1979, but the bottom line is that this work extends the idea of Turing computability from numbers or words, which are essentially the same thing, to structures in general. And the structures can be ordered, unordered, and so on. And so a good example is a graph. A graph is just a set of pairs of vertices, or set of edges, if you want. Relational databases are sets of tuples, and essentially any kind of structure is a set of stuff. And so this was the opening slide, and you have your computer with a lot of stuff in it. And here are two examples of queries. I'll read it. Give me the names of all managers with ID numbers starting with 6, first name starting with S, who make over $30,000 a year. Give me the names of all managers whose ID number is the Gödel number of a true sentence of first-order arithmetic, etc. So you smile because obviously this is a query that you would like to admit into your query language for databases. This is a query that you do not want to admit because it's non-computable, but this is the easy part of the story. The hard part of the story comes, so this is just a slide in which I defined the database or the structure, finite domain, a bunch of relations. You can give the symbols, I'll skip that. But this is the important slide in which I tried to make the point that there are many, many other kinds of queries that you do not want to allow in your most general class of functions over structures. And instead of trying to explain this, let me do it by picture. Suppose this is your input structure. It's a graph. And suppose you have two functions on this graph. And one of them, two functions on graphs. And one of them gives the following result, which is definitely going to be OK. But the other one gives the following result. And I claim that this is not OK. And it's not OK because given that this is just a set of edges, there is no reason or there's no information in this graph that prefers these three corners or these three nodes over those three nodes. So essentially this function, whatever it does on other graphs is uninteresting, but if this function takes this graph and gives you this result, it is making use of information that is not in the input. And you shouldn't be allowed to do that. If you want to put an order on the graphs, then put an order, give another relation that gives the ordering, or give some explicit order. But if this is your input, this should be forbidden. And so that's the issue. But if we change the original structure a little bit and throw these three edges out, then this becomes OK, because the input already has some thing to distinguish the top three nodes from the bottom three nodes. And even saying top and bottom here, it should be forbidden, because there isn't any top or bottom. It's just my way of. So the question that Ashok and I asked ourselves was, what is the correct notion of computability over such structures? And our answer is this definition over here. First, it has to be partial recursive, so it has to be computable in the classical sense. And the other thing, we called it consistency. It was later called genericity. The functions have to preserve isomorphisms, and that is the crucial thing. And that is the notion that turns out to be exactly what you want if you want to make sure that if you have symmetries, like in the graph that I showed you, then the function doesn't violate those symmetries because it has no information that would enable it to do so. But that's just a definition. The question that we asked was, is there a complete language? So can you do Turing computability like you have Turing machines or lambda calculus or C++ or whatever for the set of computable queries? So again, is there a language that captures exactly the generic computable functions over structures? And again, the paper was written in the setting of relational databases, but the result that I'll show you has been extended very naturally to almost any kind of conceivable structure. And of course, the question that you might be asking yourself is, what's the issue? Why don't you just take the Turing machines that satisfy this property? So just take generic Turing machines or generic C++, automorphism or isomorphism preserving programming language. The point is that even the syntax is non-effective, because by Rice's theorem you cannot even tell whether something has this property, so you can't even tell whether a program is in this language. So that makes the question at least interesting. And I won't have time to give the complete answer, but what we did in that paper, we gave a nice little language with variables, assignment statements, while, while, do, and some operations on relations, intersection, complementation, and three funny little operations which work on the arity of the relations. The down arrow just throws away the leftmost column if there is one. The up arrow does a Cartesian product with the finite domain on the right, and the twiddle thing exchanges the last two columns if you have them. And the theorem, well, we show that all these things are necessary. That's not important. This is the main result. This language captures exactly all the computable functions that preserve isomorphisms. And the hard part of the proof is essentially to use this language, given an input structure B, to use this language to compute in some kind of some way a relation that captures the set of automorphisms of the structure, and then you go on from there, and the rest is not too difficult. And that was the closing slide. Now, I decided a few days ago to add this thing, which is not directly related to computability. In a second paper that Ashoka and I wrote, we gave the basic definitions and basic results for a complexity theory and a structural complexity theory, a computational and structural, of queries over relational databases, or if you will, functions over finite structures. And we defined complexity classes, and we gave some basic results. And the closing slide had some open problems, which are all in the paper, a couple of which were solved within a few months, and so I don't exactly know the status of all of these, but I want to point to this one, in which we asked whether it's possible, or maybe in the most abstract way, is the set of computable queries, is the set of polynomial time queries over structures even RE? So QP time is the set of generic polynomial time functions, say over graphs, if you like, graphs or over structures. And the question of whether it's RE is a profound question, because it is really the question of, is there an effective language or logic that captures the polynomial time functions? And again, you can't just take the polynomial time Turing machines and make them generic, because there's no guarantee that you can effectively enumerate them. And this question is still open. And I no longer work in finite model theory or structural or descriptive complexity, but people who work in the area tell me that this is the main, it's the kind of PNP problem for complexity over finite structures. And every couple of years I meet someone in this community and I ask if there's any progress. Anyway, so that's that. And just a very brief word, with a PhD student, Tirza Hirst, 15 or so years ago, we tried to extend some of these ideas to computability over recursive structures. And so a recursive structure is infinite, countably infinite, possibly, but it's recursive. So for example, a recursive graph is the easiest definition of a recursive graph. It's just a computable set of pairs of natural numbers. So the nodes are 0, 1, 2, 3, and you can tell whether I is connected to j by an edge. That's the easiest definition. This can be extended to recursive structures in general, and we obtained several results, including a completeness result in the style of the query language I showed you earlier. You have to appropriately restrict the structures because, in general, infinite recursive relations are not even closed under projection, but you restrict it appropriately and you get similar results. And something that I spent a lot of time on, maybe even too long, for many years, was working on the high undecidability level, sigma 11 pi 11 level, for those who are familiar. Many results with many people, and just to nail where this goes. So this is the line we had earlier between the computable and the non-computable, and I'm sure most of you know that not only down here are there interesting hierarchies and structures and relationships, but also up here. This is the arithmetic hierarchy. These two hierarchies were defined by Kleene, of course. The halting problem is down low on the lowest level of the arithmetic hierarchy, and then you get equivalence and stuff like that climbing gradually higher up. By the way, when you talk about things like this to a non-professional audience, it's always very good to say, what the hell can be worse than a problem that's not computable, that's not solvable? And the answer, of course, is reduction. You don't say reduction, you say, here I have two problems, they're both above the line, but this is worse than this in the sense that if I give you this one for free, you cannot solve this one, but if I give you this one for free, you can solve it. And by the way, this oracle idea goes back to Turing, as I'm sure you know. And this is the analytic hierarchy, which is defined by second-order quantifiers, if you're familiar with it. And of course, even its lowest levels here are infinitely many levels of undecidability higher than the halting problem. And in particular, the bottom level of the analytic hierarchy is termed for various reasons sigma 11 pi 11. These are sigma 0 pi 0, or sigma 0, 1, pi 0, 1. And it turns out that while you can indeed find problems on all these levels, as you climb higher, they become more contrived, but there is an extraordinary collection of natural problems that arise in our field that all turn out to be right up here, the bottom of the analytic hierarchy. So first of all, take the Turing halting problem and generalize it in one of the following two ways. Either the non-determinism in your Turing machine or in your program is not just finite and bounded, but it's unbounded. So you toss a coin, it gives you a natural number, and then you go to the appropriate branch accordingly. This is highly undecidable. This is Kleene's basic example of sigma 1, 1. But what is very interesting is if you take an ordinary program, say a parallel program, and you talk about ordinary termination, halting, but under an assumption of fairness. So you want the printer, I want the printer. Maybe you get it twice as much or 10 times as much as I do, but we're fair in the sense, the computation is fair in the sense that eventually I will also get to turn up the printer. And under these assumptions of fairness, almost under any definition of fairness, and there are many, halting is sigma 1, 1, pi 1, 1 hard. A whole slew of results on satisfiability in various versions of context-free dynamic logic and two-dimensional temporal logic. And where's Mike Patterson? One result that we did years ago on dynamic logic with an operator that gives you 2 to the powers of 2, numbers of a's, powers of 2, all were shown to be highly undecidable. An example I like a lot is take the tiling problem of before, with a version that asks whether you can tile the entire infinite plane. And let's say you ask whether you can tile the entire infinite plane, but I'd like this tile to occur infinitely often in the tiling. Now, this should cause you to think that what's the big deal? If you have a finite number of tile types, there are going to be some of them that occur infinitely often in the tiling. But I come from the Middle East. I'm adamant. So I insist that this tile occurs infinitely often. And this causes the problem not just to be a little worse, but to be a lot worse. And I think this occurred this was first in a Fox or a stock conference. This is my last real theorem. After that, I stopped doing theory just for doing theory. And this, I think, is also kind of an interesting result. So we said already a recursive graph. These are the slides from then. Set of nodes is n, the edge set is recursive. You can also define slightly stronger, more restricted versions, but let's not get into that. And of course, they all have a finite computable representation. And there was a whole bunch of results by Richard Beagle and Bill Gazarch and many others from 72 to 86, in which they showed that many of the standard problems on graphs, when you apply them to recursive graphs, they become undecidable. And in all of the cases, they were able to nail the exact complexity on the first, second, or I think third level of the arithmetic hierarchy. For Hamiltonicity, they showed that it was undecidable, but they were not able to put it in the arithmetic hierarchy. And so a Hamiltonian path in G, you can define it in two ways. Either you start from some node and you go through the nodes once at each node forever, or it's a two-way thing. It starts from nowhere and goes nowhere. It doesn't really matter. And the path itself, by the way, need not be recursive. It's just a question of does there exist a Hamiltonian path? And so I was able to show that actually this is sigma 1, 1 complete. And I won't prove it, but it's kind of got a nice pictorial proof. You do a reduction and you build up each node into 5 nodes, and you have things going this way, and then you cut across to your neighbor and you come back again. And these are the slides in which I actually showed parts of the proof during the conference. So that was a little bit about computability, and just to wrap it up, it's not just to show you stuff that I've done, but to really point out that the stuff that I've done is really, really just taking Turing, looking to the direction in which he made such amazingly profound insights, and just push it a little bit further in the interest of extending. Now, the second part is biological modeling, and I will not get into his the kinds of equations, diffuse reaction equations for morphogenesis, but he was interested in growth. He was interested in how things form their patterns, and how could we build a model that would explain it. And so I've, for 15 years now, been working on many different topics in modeling biology using ideas and techniques from software and systems engineering, such as the state charts language and others. But I want to show you examples of two of those projects, both of which have to do directly with growth and forming patterns. One of them was modeling the growth of the pancreas, and a much more recent project that we haven't published yet, but I'll show you a sneak preview, is modeling a tumor, a cancerous tumor, also thinking of it as growing an elbow or a tail or a pancreas for that matter. Actually, this looks a little bit like what I used to look like in the, I think. All my work in biology is done together with at least one very good biologist. I don't know enough biology to do any of this on my own. I know there's always at least one PhD student or postdoc. This is Yaki Sethi, who did this work with Yuvaldo and Yaron Cohen with us. There are several publications, but that's the main one. And so the pancreas is one of those several organs that we all have. This is a mouse, but we are not that different in that respect, which grow out of the gut, which is that pipe that eventually links the mouth with the rectum. And the pancreas, it has two parts, an upper and a lower, but it starts out like a bud, and then it kind of grows. And it ends up looking very much like a cauliflower or broccoli. This is a cross-section of a pancreas between these two stages. The green is the code for pancreatic cells that have a lot to do with insulin generation, and the red are non-pancreatic cells. And I'm going to show you a link to a pre-recorded video of our model, but I would really like for you not to think of this as just an animation, a video that you prepare to explain. This is the outcome in real time of a model running in which you can make any changes that are doable in the program itself, or even via the animation. You can freeze and change properties of cells, and it's completely interactive and executable. It was a project that took 5 years to carry out, and the main idea was to build a program for using state charts, but that's not the point, of a cell. When people ask me, so what's the big deal? You take information that biologists tell you and you put it. No, it is a big deal, because the analog would be to write a program for a person, and then to throw 120 people into this hall, and the emergent behavior would be a lecture at the Turing conference. And that's exactly what you want. You want to program a cell, and also we program some of the blood vessels around and things like that, but then you throw several thousand cells on the screen, and it grows into a pancreas. And that's the crux of the issue. And the ideas are not based exactly on Turing's equations, but the motivation definitely comes from him. This takes a few minutes. I'm going to kind of jump it forward. There's one point. So you notice, by the way, that it starts out all non-pancreatic cells, and then the number of pancreatic cells, or the ratio, grows. And we can halt this at any point. In this case, I think we halted and gave cross-sections in a minute. Yeah. Let me freeze this for a moment so you get to see the similarity with the real thing. And then I'll drag this forward a little bit more. It just gets more elaborate towards the end and gets to look a lot more like a cauliflower or broccoli. And just to intercept the question that often people ask at this point, so did he discover anything new? Yes, the fact that you can publish a paper like this in PNAS means that you have to have made some biological discoveries too, and that's the whole point. But I want to, so this is the model in running at various stages, and what you see under the microscope. And you can also measure, and you can count the number of green cells and red cells and compare that with what people know and so on. But I want to close this little example with the following anecdote. After this project was essentially done, Yaki Sethi, who was our PhD student, came along and asked, why should the pancreas look like a pancreas? So we made all this effort to program it in a way that, but a liver, which also grows just not too far from that same point on the gut, looks like an American football, and a lung looks like a very highly branching tree. If you take cells that will turn into pancreatic cells or liver cells or lung cells, and you look at them closely, they look the same. So what makes the difference? And there was some hunch that it has to do with blood vessel density. So we made some wild changes in our model playing with the density of blood vessels. And we were able to have the same model growing to look like a pancreas, to look like a liver, or to look like a lung. And there is experimental confirmation of at least part of this hunch already done a few years ago in Yuval Do's laboratory. So this is an example of just building a model for the sake of building a model, not to particularly answer a question of whether this gene affects that process, but just in order to understand, as in fact Turing had advocated, to understand how patterns form and how things happen. The second piece of work, which is in progress, and Amar Bloch is a PhD student, and we're not working with one particular biologist, but we're consulting with several, and again using state charts. I'm going to show you a sneak preview of this. The graphics is kind of crude, and the running is kind of slow, but there's an enormous amount of biology that has gone in. This is already 2 years plus in working. These are a very crude portrayal of blood vessels that kind of surround this growth. I'm going to drag this forward also, make it a little faster. And at some point, these blood vessels start doing their deadly thing, which is to say, aha, I'm going to go in there and feed more blood and make this thing grow even faster and become even worse. So again, you get leave it a few more seconds so you get to see what's going on. Here, no biological discoveries yet, but we're gaining, I think, what might turn into a deeper understanding of cancer growth, and especially the role the blood vessels play in helping this devastating process take place. Now, over the years, I've advocated for what I think is the correct grand challenge in this area of modeling biology. A lot of people say, you know, you talk about an organism, why don't you just talk about a cell, which is hard enough? And it's not because I know how to do a cell, it's because if you really want to understand life, you want to model an elephant or a worm or a fly. And so we sometimes call this the whole organism process. So in your introduction, you mentioned biology, and I get people asking me, so when are you going to finish modeling your worm? So the challenge is to construct a full, correct, you have to define these, or at least give the framework model in 4 dimensions, so 3 dimensions plus time, true to all known facts. That's a very important point. You want it to be the case that everything that's known about your elephant somehow gets put into the model and weaved into the behavior. And I think the right level in which to aspire to is a multicellular organism. Which animal would be a good choice? I have my own preference, which is the C. elegans nematode. And I'm not actually leading this project at all. I'm too old and doing too many other things, but I hope this will be done. It's an extremely non-trivial, even though C. elegans just has a little over 1,000 cells, we spent 8 years working on 6.5 cells, 6.5 of the behavior of another crucial cell called the anchor cell, with some relatively simple processes, which is the forming of the vulva, the sexual opening where the eggs get laid. And we also, at the same time, did another smaller project, which is very closely related. And we weren't even able to put the two together because the languages were different, the level of abstraction was different, so we even gave up on that. To do this properly, you really have to solve some major problems of level of abstraction on the level of pathways and signaling networks and pathways and motifs, all the way up to the intercellular communication, which you might do using a state chart approach or something like it. It's incredibly difficult. And this grand challenge will feed into the final topic here, which is AI. And of course, when I'm not an AI person, what I mean here is the Turing test. And so I don't have to explain what the Turing test is, and I will definitely not get into the arguments about how profound it is, how plausible it is it the right way? You know, I don't philosophize. It's my older brother is a philosopher and historian of science, and he gave a talk many years ago at our institute, and I introduced him by telling the story of Descartes, who, when he was a small child, he told his mother he wants to become a mathematician because then all he'll need is a paper pencil and a waste paper basket for the garbage. But then a year later he said, no, I want to be a philosopher because I will not need the waste paper basket. So I won't get into any of this. If you pass the Turing test, is the computer really intelligent? Can it fall in love? Does it have consciousness? None of that stuff. But my little follow-up here, this was published in a Nature journal in 2005, is a Turing test for modeling nature, for example, for modeling biology. And let me just tell you how it. So this is the Turing test. So you have a human or a computer here, a human or a computer there, and a human interrogator linked by wires for the obvious reason. You don't want to be able to smell or hear or listen to. This is the buffering mechanism over there, and we all know what the test is about. And what's that got to do with us or with this work on biology? Okay, so I said this already. So here's the issue. If you're doing classical standard kinds of bioinformatics or systems biology, and there's incredible work, as you all know, done. In our institute, there are 2 or 3 of the best people in the world doing this kind of work. And they start with a question or a set of questions, and then they might build a model to give some predictions, some answers to questions. And then they go to the laboratory, and they do this back and forth. And the question of when you're finished is obvious. You're finished when your predictions have been confirmed in the laboratory. And then you can throw the model away, and you've made your discovery, and you go on to the next set of questions. But if I say I want to model the weather, or I want to model an elephant, or I want to model a C. elegans nematode, or a liver, completely, not just how it grows, the question of when you're finished is really the main question. This is the crucial question, because you don't, when we want to build a model of the worm, we're not starting with a question that we need an answer to. We just want to understand worms. And it's a little bit like, oh, we see a worm, how does it work? It's a little bit as though you walk down the street and you see someone taking money out of an ATM, a bank machine. You've never seen a bank machine in your life because you keep your money under your mattress. And you stand there looking, and you're given a month to stand there looking and take. You can't open the thing and look what's inside, and you have to understand how it works. And by the way, my personal ATM has a little dwarf inside who lights up the pixels and pulls in your card and very quietly calls the bank to see if you have your $100. And if you do, pushes out the banknotes. And you can chuckle, but try to figure out an experiment that will prove this wrong without opening up the machine. It's not quite trivial. So, but this is the main question. If you're trying to model a piece of nature, you need a criterion for when you're done, when your model is valid. And as I said, in conventional modeling, you address specific questions, and so the model is valid and complete when the predictions are verified in the lab. But here, comprehensive modeling of a full, like this whole organism project, is to understand the whole thing and not based on any specific questions. And one of the things that you can say about an ATM or a worm or an elephant is that you can claim to have understood the way it works and how it behaves if you can build an interactive simulation that does exactly what the real thing does on its own. And of course the question is now, how do you tell when you've managed to do that? And you can guess the answer. We want this idea of making a prediction for a certain question and confirming it in the lab. You want to take that to the utmost limit, because you, building the model, have no idea what questions you might be asked. And so you really want a Turing-like test for modeling biology or modeling nature in general. But there's an interesting twist here taken from Karl Popper's philosophy of science, and with or without the waste paper basket. I think this is a very profound observation of Popper. So here's how it goes. We're done when a team of biologists, so let's say we're doing a C. elegans nematode. So we want the model to be so good that a team of C. elegans experts will not be able to tell the difference between a real worm and the worm or the bunch of worms in the model. And well-versed, of course, is taken from patent lawyer terminology. So here's this Turing test. You put your elephant, not the elephant, but an elephant laboratory in one room and the model in the other, or your C. elegans laboratory. And here is a bunch of experts who probe. You know, what happens if I step on the foot of the elephant? What happens if I turn off this gene? What happens if I make the following, ask the following question? And some of the questions, of course, this person might know the answer to, some he might not. But that's not the point. The point is, you know, if I'm trying to ask questions, or in the classical Turing test, I can ask questions, you know, that I do not know the answer. But the whole point is to give the impression that you're the real thing. Now, obviously, if these experts in the interrogation room can't tell the difference, then the model is refuted and it has to be changed. But the crucial point is the following. So let me put it this way. If this laptop is subjected to Turing's original test and passes, we'll all get very excited, and you can stamp it in permanent ink. This laptop is intelligent, or at least is intelligent a la the Turing test, and you can use permanent ink because the notion of intelligence will not change. Knowledge will change over the next months or years, but not the notion of intelligence. But if this laptop passes this test, the elephant test or the worm test, you can stamp it. David's laptop is an elephant, or is a theory, a valid theory of an elephant, but do not use permanent ink, because tomorrow morning we will be discovering new things about elephants that we did not know, and we will have to change the model. Not only is that the case, but that's the motivation. The motivation is, so you remember I have a dwarf in my ATM. Some of you, that makes you angry, especially if you're convinced that I really believe there is a dwarf, and the only reason you can diffuse your anger or your whatever your feeling is about the statement is to devise an experiment that will show that this theory is wrong, and then I'll have to change the theory. This is what Karl Popper has taught us. So this refutation of a model that passes this test will happen all the time, and that is exactly the point. And I can, without getting into details because I have to finish, this thing is happening even in our own very, very modest biological projects, where there was one case where we had these 6 cells, and there was something that could be done by a single cell, but could also be done twice by 2 different cells, but never by neighboring cells for some reason. And it seemed to me that this was a kind of dining philosopher's phenomenon. So in the model, I asked my student to put in a little dining philosopher's mechanism inside, as though in between each of these 2 cells, there is something else that prevents the 2 neighboring cells from doing what they were supposed to be doing. And the biologists got very angry. They said, there's nothing there. Here, take a look. And I said, I don't care what you say. There is something there here, because now the model works and satisfies everything that we knew from the 1986 papers that we found in the laboratories. And they got really so upset by this, and I did this deliberately, of course, that there was a series of experiments carried out over 6 or 8 months, and we discovered what was really going on there. There was some timing, subtle timing cascade of signals that caused these 2 never to be able to do the same thing. But this happened because I told them there's a dwarf in your ATM, and they got upset. And this is Karl Popper's philosophy of science in actual operation. You put a theory forward, someone else, Einstein clobbered Newton, quantum theory clobbered Einstein, and so on. Those are the big examples, and we have many small examples. And of course, you need a better buffer, not just wires in a separate room, because you can ask a question of a model that will take a split second on a computer, but might take 6 months in the lab, or might not be possible in the lab at all. You need another bunch of experts to buffer away those differences, just so you get the clean issue of making the probes. Do not take this too seriously, just like I don't think Turing's test in the 1950s should have been taken too seriously as something to strive for tomorrow morning. Maybe not even realizable at all, but I would like to claim that if you are willing to buy into this idea that it's a good idea to try to build a model of a complete biological system in order to understand it properly and therefore understand life, then put that on the horizon, even if that's not possible to a large extent, then right next to it on the horizon, the criteria for success should probably be something like this version of Turing's test. Commercial break. So these 2 books, Algorithmics and Computers Limited, both, I have some copies of the 2012 printing of this in my room, but I forgot to bring them. This talks about a lot of things related to the first topic, the limitations of computing. Do I have 3 more minutes? So I'd like to end by showing you a video. I've shown this many times in the last few years. First of all, it's fun, and it's got music, but it's it doesn't pass any Turing test, but it's a wonderful example of how you can make things really so real. So it's not interactive, therefore it doesn't pass the Turing test. It's just a video, but so the music is real. It's played by real people. The animation is artificial. Maybe you've seen this, maybe you haven't, but it's a pure joy, and I love seeing this. And when you're looking at it, just take a look at how wonderfully the physics and the light and the shade and how real it really looks. If we can do something like this, which would be interactive and model a real piece of nature, then we're in a very good situation. Is that too loud? Actually, the point in relationship to what I was just talking about is that this is not how the music is really played. There are people that are doing stuff, but it's an imitation. And as long as you haven't shown me what's really going on, this is what's really going on. That's the point. Not only the graphics. Thank you. Thanks. You have to see this more than once to notice that even those, all those things, they have varying lengths, which reflects the pitch. You know, it's really amazing. Okay, thanks.
Any questions?
Go ahead and,
Sure.
Which end? Oh, this end. David, thank you. Very stimulating talk. Just one small point. I didn't see why you were confident that the results of the Turing test on a human should be written in permanent ink.
Should be?
Should be written in permanent ink.
It's not so much confidence. It's just that the notion of what makes someone intelligent is not something that will change in the near future.
Well, why not?
We're not out there to discover something new that makes intelligence different tomorrow than it is today. There is knowledge that, I mean, something will happen this afternoon that you will hear about and I will not, so tomorrow you will know something that I don't, but that's not intelligence. Intelligence, you know, moving around in the world, understanding what's going on, is very robust. Whereas what we know about a piece of biology changes all the time.
Two very quick questions. Are your cells different from, say, Stephen Wolfram's cellular automata?
Yeah, they're very different. The way we model a cell is the way you would try to model, say, a person. You would say, okay, so a person can be awake or asleep. If he's awake, he's sober, or half sober, or non-sober, hungry, and so you build up a state space, very structured. In particular, we use the language of state charts, but that's not the point at all. And we go top down and sometimes bottom up to describe the behavior of the cell. How would the cell respond to this particular thing? So very often you have real biological data that you have to put into a differential equation, but a lot of it is discrete reactive, and we use standard, automata-based techniques, sometimes scenario-based techniques to do this.
Other quick question. Carl Chulik gave an example of tiles which tile but not periodically. Did you place periodicity in your hierarchies?
No, I haven't done that, no. So the question of whether a set of tiles can tile the plane but non-periodically, I don't know. My guess would be at least sigma 1 hard. Just based on the fact that even to tell whether a tile repeats is sigma 1 hard, but I would have to go and think about it.
Oh, that animation was done by one of my students, Wayne Lytle.
This one?
Yeah, the musical one. His mother is Norwegian, but you can make him an honorary German. He's very much a stickler for precision, and all those motions are actually driven by the music with a precise timing. It's a unique thing.
Can you send me, is this someone I can correspond with?
Oh yeah, I've got, well, he doesn't have a public address,
you can send me an
email address, but I can send it to you. I'm sure he'd like to talk to you.
There are several others, by the way. Did he do them all?
Oh, he and one other programmer basically have done everything together. He's both a visual artist, musician, and computer scientist, all rolled into one, a little unusual thing. Interesting guy, very humble guy, very it seems to me, in a way, there's an analogy between what you've said about the biological modeling and last night's discussion of the Riemann hypothesis, that maybe somewhere there's some exceptions that are along the timeline that we can't access right now. But I do remember some years ago, and I don't have the reference for this, there was a psychologist from Toronto, I believe, who had some very big questions about the Turing test. He was not comfortable with it. I don't know what that is, so I'm just throwing that out as something that, somebody might want to look into. But he had, coming as a psychologist, not a computer scientist, he had some serious issues, and I don't remember what they all were, but this paper was probably about 10 years ago.
Oh, there are many people who have issues with the Turing test on many different fronts. I can imagine that being the case, definitely.
Yeah.
So I have a question about the modeling, and in particular, what fraction of the information that you used to construct that model came from facts known by biologists versus tuning some parameters with some kind of learning mechanism?
Much more the first than the second thing that you said. But it's not easy. It's not, I like to say it's not, some biologists, they look at this and say, okay, so you put the data into your computer and it runs. That's stupid. The pancreas model, we had about 150 papers that we had to read. And the papers say things like, this happens, then this happens in 70% of the cases. And these are papers that describe what happens in the laboratory. Most of these things have to emerge out of your model. It's like the example I gave. You can say a lot of things about a lecture hall. You can describe a question answering session and the clapping and the people walking out when they're bored and so on. But to program, the way we program the system is to program a person. All this has to happen as an emergent property. So we use a lot of information that we get from biologists. We work with the biologists, a lot of trial and error. And there's also some analytic stuff on the lower levels. But it's really a thorough and often very frustrating effort of trying to understand what the cell does when it wakes up in the morning and why does it do that. And again, the idea of the Turing test is true on all levels. Even after working for a few hours on the beginning of the model, you start running it and you see if it's doing the right kind of thing. That's the imitation. And the right kind of thing. So the first thing that our pancreas model did for months, it just collapsed. You know, the thing started plop, plop. Just didn't do a thing. It didn't even grow. And then it grew and blew. And you know, and then you gradually, with the biologist, try to understand what is causing it to grow in this way. And they say, well, maybe this, maybe that. You put in some more information in the behavior.
One more question.
Could I ask you a question about the model that you have on the music? If you had actually built that machine, I know it was an animation, but if you actually built that machine, would it actually have worked, or was this just intended to give you a notion of the animation? And if it was actually accurate,
well, he should know.
How would you compile the animation to get it really accurate if it was one-to-one accurate with a real machine that would have done that?
I think you should know, but I think my answer is more important because I have no idea. And I'm just a bystander here. And I think that if you have the machine throwing the balls out from the bottom the right way, it will probably work. At least that's
my question is not whether it would work, but whether what you actually showed was the model of what would work. And if so, how did you compile it?
I think what they showed is just an animation.
Maybe I can answer some of that. By the way, I just remembered something interesting in terms of the history. Wayne's mother has a math degree from MIT, and she was one of the first programmers in the world. She worked at Aberdeen in the mid-50s on the ballistics calculations. So the ballistic, I don't think that was catching, but he starts with the music. When he had a band here in Princeton. He grew up in Princeton, by the way, and he had a band, and he was quite a stickler for getting everybody synchronized as tightly as possible, all the different instruments. And so that carried over into these animations. Now, of course, there's no visible means of locomotion on these parts. So if you have a part moving around, there's no motor on it. It's just an animation. But what is correct is the timing. And of course, there's no statistics in the thing, too. So if you push a ball up, it may or may not hit where it's supposed to go, but it always does in the animation.
I don't think I agree with the thing about locomotion because these are freely shot and falling balls. That's all that's happening, and springs. If you had a machine underneath the surface that would just shoot out these balls with the at the precise time, with the precise velocity and power, you could definitely get this. There's nothing moving around in the air like Harry Potter. It's not Quidditch.
That's right. It's all done with, he has a software that takes the drive from MIDI and produces the, well, of course he draws the animation and has to define what each instrument does, but there's no dither in the ball. It's not a real ball in the sense it's an ideal thing, but all the motions are in fact mathematically correct, except they don't have the real perturbations that a real...
Of course, an interactive version of this would answer many of your questions. So you put in your hand, you take out 3 balls, the music changes, you kick one of these things, it changes again. This would be the real test. To build not an animation, but a reactive system model.
It's kind of slow. He's got an array of about 20 nodes that render this animation. It takes days to do it.
I think there are lots of interesting questions, but maybe we should move on to the next talk.
Thank you.